Time was not my idea. I had no input. Secondly, I wasn't aware I was going to be filmed. I would have worn matching clothes and combed my hair if I'd known that was the case. But here I am. Okay, this is as said in the introduction. I've worked reliability for many years. This is work that's done primarily, although his name doesn't show there, by a graduate student that's working with me by the name of Peng Wang. And actually Peng, although he's just months away from defending his PhD dissertation, he's already working for United Technologies up in Hartford, Connecticut, working in reliability of fuel cells. The issue here is reliability prediction. You know, as I was saying to somebody beforehand, if we could lump all problems into two categories, which we can't, but if we could lump all problems into two categories, those that are already very reliable and those that are not very reliable. Now, your intuition, if you said, now where would most effort be dedicated of reliability engineering? Your intuition would say, well, obviously, to those problems that is currently not so reliable. That's what your intuition would say, right? The ones that are already reliable, well, they're already reliable. Your intuition is wrong. Your intuition is wrong. In fact, most of the activities in improving reliability and optimizing reliability and achieving reliability at really high levels are systems that are already pretty reliable. So why would that be? It's because it's systems like satellites where you need a really long screwdriver to fix them, or the space shuttle, or airplanes, or telecommunication networks. Systems that are already pretty reliable, but are they reliable enough? And I think as the complexity of systems increases and the technology increases, the answer is no. And so here's the dichotomy. We need to do reliability studies on things that are already really reliable. And so where are we going to get the data? It already takes a long time to wait for something to fail. And yet we need to continue to improve it. One approach is what I'm going to be talking on here. This is using degradation modeling, which for one class, or a particular class of reliability problems, is an answer to some of these dilemmas. How can you, this is going to sound maybe naive at first, how can you predict reliability or make assessments on reliability when you have not even observed a failure? And once again, you could say if you haven't observed a failure, maybe it's reliable enough. But in many of those examples I talked about, and other examples, imagine a heart implant or other types of medical electronics, is that we want to continue to improve reliability. One solution or possible solution is what we call degradation modeling. There clearly will be examples where this will not work, and I don't mean to imply otherwise. But there are examples of particular parts, systems, and failure mechanisms where this will work. What do I mean by degradation? There is some observable and measurable condition in which you can anticipate when a failure will occur. Now, is this set to... Here's some examples. Drug stability. A resistance drift is what we did in the cave meeting over the last several days. Crack propagation. There's many types of examples as well. Here's one. We're looking at fatigue cracks of some materials. We can detect prior to failure the emergence of some of the fatigue crack. Here's another one. This is interesting. This came from a student in my class. I teach about every other year a course in generally every year I teach some course in reliability engineering. I don't know if you know what a stent is. I did not know myself until this student came in. A stent is something that's put in your arteries in order to keep the arteries from closing. Okay, what happens is that the stent, which is kind of analogous to a fence, meaning there's gaps in the stent, and the tissue will come in through those gaps. And so the stent, which is put inside your arteries or veins, or actually I don't know the right term, is not permanent in the sense because the tissue will grow in. So they have coated the stents with some drugs to prevent that from happening. But the drugs have limited, not shelf life, have limited utility. In other words, they don't stay effective forever. This is some actual data. for the student in my class who works for Cordis, which is a Johnson & Johnson company that manufactures this stent and develops this stent technology. It showed, I don't know what the units of time were, as time goes on, the potency of the drug degrades, and it's going down to some failure threshold at which it will no longer be effective. Now, here's some other example. This is a timing belt. Okay, what we're trying to do, let me go ahead one. Well, I'm not ready yet, is use this as an alternative for the collection of empirical data. Now, don't get me wrong. If we can put a bunch of units on test them to failure, observe the data, do distribution fitting, fit Weibull distributions, exponential distributions, whatever, that's the preferred approach. That's the preferred approach. But we're dealing with things here that are highly reliable, and we may not observe failures. And to make matters even worse, even if we accelerate the environmental conditions, we still may not observe failures. And yet, as I said in my introductory remarks, we're dealing with things that if they fail, perhaps there's loss of life or major system loss, very dire consequences of failure. So the fact that it's already highly reliable doesn't mean we don't want to continue to make improvements. Okay, the advantages of this degradation data in the cases where it holds is I can get fairly plentiful amounts of it. Consider this kind of overly simplistic example. I have 3 components on test. Okay, on the left-hand side, I test. 2 of them fail. The X is a failure. 1 of them has a censored data point. Now, so there, I have 3 items on test. I got 2 times to failure and a censored. Same 3 items on test, or maybe a different 3 from the same population. If I'm looking at degradation data, and again, what is degradation data? Not a time to failure. It means there's some observable or measurable condition, and deterioration of that condition towards some failure threshold shows me the rate at which I'm getting closer to failure. Notice, I have 3 items on test. I have 12 data points. Now, of course, there's going to be some issues of dependency and other things. But the point is, without observing a single failure, I can generate a fair amount of degradation data where I have very limited access to time to failure data. The whole thing kind of started, this idea of predicting reliability based in trends in degradation by Meeker and Lu, which were statisticians at Iowa State about 10 years ago. And I've got this somehow set to, and you can see there's some examples here. Okay, now, what we see as time goes on, and these are different degradation paths, we notice the distribution of the paths is increasing. I'm not saying that as it will always be the case, but often it is. As these different systems are exposed, we're seeing the paths get diverge. Okay? Once again, as they reach any individual path, this failure threshold, a failure occurs. So if we think of this graph, now I know some people have told me this can be confusing. These distributions, which look like normal distributions, but they may not be, they're coming out of the board. So think of this as like a mountain ridge, if you will, that follows along that path. At any point in time, and notice that the variance of these is increasing with time, not always the case, but many times it is. The area in the tail of this distribution beyond the threshold, that would represent the probability of failure. So if in the early points in time, well before we actually observe any failures, I can characterize that distribution for any fixed time t, and then try to project that distribution, not just the mean, but the whole distribution as it's shifting with time, then I can make reliability predictions throughout. And perhaps I'm doing this early on before any of the paths that I observed approach that failure threshold. And here's where we see what I just said. The reliability curve, which is my end result, represents 1 minus the tail probability as it goes beyond that threshold. So I can make reliability predictions based on projected trends in degradation. And I think this says just what I've said. If reliability is defined by definition as the probability of some random failure time, capital T, exceeds some fixed or specified mission time, little t, capital Z, which I haven't talked about yet but will shortly, that's a vector that represents the environmental conditions. I haven't really talked about that. But we may have the same part being stressed at different environmental conditions. It may be thermal cycled at one rate, and then the same part may go into another application where it's thermal cycled at a different rate. For now, Z just represents some specified environmental conditions. So the reliability is the probability that the random failure time exceeds my mission time, but it's also, for a fixed T, the probability that my random degradation measure, and the distribution of that measure, of course, is for fixed T, because it'll change as T changes, is less than the threshold. And if that's the case, all I need to do is characterize the probability density function not for times of failure, but for the degradation measure for fixed T and fixed vector Z. So if I can do that, I can make a prediction of reliability. Now, so if I'm going to take this approach, and I want to emphasize, what I've discussed so far is not anything new. It's not what I did. It's not what Peng did. I'm bringing you up to date on work that started about 9 years ago. To do it, however, I need these steps. I need to come up with a model of that failure criteria, or the degradation phenomena. I need to define at what point is it a failure. I need to establish the relationship between degradation and time to failure, and then I need to come up with some way to predict reliability. There's three general ways to do that. We've focused on the first two. Not that Markov chains is not a perfectly acceptable way to do some similar ways, but there's, for the problems we've been working on, there's some difficulties. Apparently I have this set to advance, and I meant to turn that off, but we'll persevere. The two primary ways is what a general path model and then something called a degradation hazard function model. I don't have time to discuss either of them in great detail. I'm going to review them. I'm then going to review some of the work we've done recently in this area, and then I'm going to conclude this talk by presenting three research issues that have yet to be resolved. In other words, that are waiting for someone to resolve. Some things that if I get around to it, I may resolve, but then again, I may not. Okay, this is the very first work. Meeker, if you've done work in reliability, he's someone, a statistician at Iowa State, who's written some books on life data analysis. Now, I'm sorry to confuse my notation here. F is not a probability density function. It's just any function. It's just some function. And what Meeker's model shows, he has a general model, and then as time goes up, this degradation model goes up. But he has two types of parameters in that model, phi and theta. Phi are the fixed level parameters, meaning we may not know what they are. We can estimate them, but they're fixed for the whole population. Theta is random effect parameters, so that the parameters which govern my degradation model are themselves random variables. So you can imagine some physical model that shows the degradation changing with time. Some of the model parameters are themselves random variables. This is Meeker's original data. This is crack propagation. We see starting from this time, we observe these different individual paths. The dispersion or the variance of those paths increase with time. They have a degradation model that is in fact based on a physical model. So it's not an empirical model. It's not based on simply collecting data and curve fitting. It's based on some physical failure phenomena. This is a very good approach. However, it's cumbersome to use. Additionally, it's only for a fixed environmental vector. In other words, if I collect data under one series of conditions, I can use it for that series, but I cannot convert from one to the other. The estimation of, in this instance, my cumulative distribution function, which is 1 minus my reliability function, has to be done by simulation. Confidence intervals are done by a bootstrapping type method. which means even once I've completed the analysis, I don't have, and this isn't all that bad, but I don't have a repeatable method. I need to conduct a simulation every time I need to do a reliability analysis. I need to do bootstrapping to get confidence bounds around that. While this was a good starting point, clearly it's just one way to do it. The next way, which is by El-Sayed, he's a colleague of mine. He's a senior faculty member at Rutgers, Industrial Engineering Department at Rutgers. Hussein Iqbali. Hussein Iqbali got his PhD from Rutgers. He now works for the FAA doing reliability work on safety work, really. He does more. He's kind of moved from reliability into kind of a safety mode. But this is based on a new concept called degradation hazard function. I'm going to have to, if you know what a proportional hazards model is, which is probably maybe a few of the faculty members, I don't know. If you understand that concept, then you'll probably understand that. If you don't understand that concept, I'm going to have to kind of go over high level. But this is a different way to do the exact same thing we discussed with the Meeker and Lu model, where they developed this a degradation path. Now, the reason the Meeker and Lu model, the paths weren't all the same, was because the model had parameters in it that they themselves were random variables. So the paths dispersed. What the degradation hazard function model tried to do is characterize the whole probability density function of the degradation path for fixed t and fixed bold z, where bold z is the environmental stress vector. In time, we're not going to want z always to be fixed. We're going to want to investigate different values of z. So this is, it's two people from Rutgers. I probably was at one point biased, not intentionally. There are people I knew. Their approach has specific advantages, but now we've been testing it and using it for 3 years. We realize it's not a panacea either. There's some disadvantages to what they do, but there clearly are some advantages. So there's these two primary approaches, the Meeker and Lu and the degradation hazard method. And let's first look at this expression. And we're just saying here, I can relate reliability, it's a function of capital D, which is my failure threshold, to something here, and I'm not going to define it only mathematically, called a degradation hazard function. It is not the same as a hazard function for time to failure, if you know what that is, or an instantaneous failure rate. If you've worked in reliability, and I'm sorry that keeps happening. I'm sure I set that myself unintentionally. We've made the assumption, and this assumption that's been tested and needs to be continued to test, that I can split this function. Now once again, what is it? This is an input into my reliability function, but it's conditional on t and z. It's conditional, so for some fixed time t, I'm kind of trying to characterize that probability density function for a fixed environmental vector z. But the assumption, which is analogous to proportional hazards, is I can make this a multiplicative function of x, which is going to tell me for fixed t and z, it's going to tell me the shape of that distribution. If we can think of that path increasing, I had those distributions. Q of t is a function that's going to show how that overall that distribution shifts with time. And we notice those normal distributions change. They don't have to be normal. In fact, one advantage is here, it could be anything. exp, and those are two vectors, beta and bold z. That then shows how the whole curve will shift as I vary z. In other words, I've maybe put it under more stressful conditions. The key is, though, how do I determine those three functions? G of t, Q of t, and how do I estimate these parameters? Beta. And that's what Hussein Iqbali's PhD thesis was involved. And he did quite a bit of work. And I guess I'm not going to go into that much more specific. I do later. But he came up with a very detailed likelihood function such that we could estimate some of those parameters. A third method that absolutely would work to do this, although we have not pursued it, because for what we're trying to do, makes this actually an inefficient approach, but it's theoretically sound, absolutely sound. If I can take this degradation path and imagine all the stages between a new system and that failure threshold, and I'll kind of discretize into various sub-degradation levels, I could treat this then as a Markov chain as we progress from level to level. The issues, of course, are how do I define, because in practice it's a continuous degradation. But if I could define some of these sub-levels, I could in fact do this. The difficulties with these is to determine all these transition rates. This is a hard enough problem to begin with. If I had a lot of data, I in fact could do it. I could do the whole problem this way, and it would be a theoretically sound way to do it. It is not the approach we've taken. This approach maybe we will take in the future. Okay, starting with the original paper by Meeker and Lu. This is work without stress factors. What do I mean by stress factors? Vector z is implied to be fixed. In fact, you wouldn't see vector z in that work. The implication is that we have some sort of environment with which this component is being used, and it'll always be that environment. And furthermore, it implies we're not accelerating. Now, why is that create problems? Well, for many instances, it does not create problems. But think back to my very introductory remarks. We're dealing with things that are highly reliable. It's hard to observe failures. Therefore, it's also hard to observe some of these signs of degradation. So often we do want to accelerate. We do want to test under one vector z and then translate to a less stressful vector z. Nevertheless, this is some of the work that's been done without stress factors. Something I have not talked about, but I will, is the failure threshold. All the previous graphs I showed that failure threshold. Imagine our product is an illumination panel that goes into your car. And the illumination degrades with time. The light intensity degrades with time. Now we know as it degrades to a certain level, it will become unsatisfactory for you to use and it will become a failure. That's, of course. But now let's say I need you to define specifically the level at which a failure occurs. And the companies that make those panels do just that. But is it a number that is really true for the entire population? If you're using it in, I don't know. I visited Norway once, and when I was there, it was only light for 4 hours a day. I imagine that would be different than if you were in the equator, you know, where the sun is. But the point is, or maybe the difference between you and me. Maybe our ability to perceive different light emissions or different light intensities are different. So the failure threshold, these models, with the exception of the last one, assume that it's constant. But one thing we're going to look at with just a few slides is what if it's not constant? What if it's also a random variable that varies from consumer to consumer? Or perhaps we're making light emission panels and one's going into trucks, one's going into farm equipment, one's going into, I don't know, something else. Maybe it's the same illumination panel. I'll tell you right now, though I'm getting ahead of myself, users, if they're forced to pick a constant, will either pick a mean value or more often, think about it if you were developing this, a worst case. As soon as our first consumers begin to lose the ability to use these panels, we'll call that failure. And that overall, considering the population, will cause you to underestimate the reliability, and we do show that later. Now, more recently, this is with stress. And you'll see, and I think, you know, I'm not claiming we've looked at every article. There's always one additional article. But we've done a pretty exhaustive search. And these tend to be, and you notice most of them are fairly recent. There's one in 1992 of people who have looked at, researchers who've looked at degradation modeling with that z vector, or with stresses. But once again, so as you see here, this isn't work we've done. We're trying to extend some of this work for some more complex cases. So here's a summary. And this was one of the major points of this talk, to summarize the work that's been done. There has been work on degradation model, and we want to emphasize that these models work great under their intended usage. You know, a problem of researchers when they're extending someone's work is to criticize. But in fact, there's no criticism. It works great. for what they intended these models to do. However, we're looking at other applications where maybe they don't work so great. They almost always, and this is the previous work, assume a constant failure threshold. They also make an assumption about the initial degradation measurement. That's less important. The stresses are known to be constant, deterministic, and it's a few other points, but those are the key. Now, if I take these methods and I want to apply them to fielded systems, when you're in a laboratory and you have a thermal chamber, temperature cycling chamber, vibration, I mean, you can set those and you know what they are. You can measure them, you can observe them, and you can apply these models. When you're in a fielded environment, things are more random and they're changing and you can't control them always. So the point of the work that we've done here is try to extend some of these models for this, the less controlled but more important field environment. So here is some of the extensions that either we have done, most of these were complete, or some of them we're still working on. We want to look at random failure thresholds, when the failure threshold varies throughout the population. We want to look at changing stresses. For example, we might model, let's say, a system that's being used up maybe where I'm from, up in the northern part of New York State. That's where I'm from originally, where maybe during the winter you look at some sort of a temperature cycling profile, and in the summer something very different. And yet the models imply some stationary stresses. Okay, the models won't work for that case. So we want to extend them for that. We also want to extend to system level modeling. What we mean by that is, let's say we have a component. If the degradation paths for all the components in the system are independent, then I can use reliability theory very quickly. But what if they're correlated? In other words, what if on one system, if one degradation path is going towards its failure threshold more quickly than the mean, maybe they all are. And maybe the reverse. How can I extend failure mechanism level conclusions to the system level? It's another thing we've worked on. We don't claim to have a definitive way to approach that problem, but we have come up with approaches to it that do work under some instances. And then there's some open issues as to how you would actually then use these models. Let's say now you're not dealing with a system that already exists, you're designing a new system. And these are observable and measurable degradation measures, but only if you have something there to monitor them, right? And furthermore, let's say you cannot afford to monitor every degradation path. Then it becomes an optimization problem. What's the most effective way to place these measurement devices? How often do I measure the data, etc.? And this is an issue that I'm going to present at the very end as an open issue. I don't know how to do it yet. Maybe somebody in here can tell me how. But we've been working on it. Here's the first one. Random failure thresholds. There's the example I talked about with the illumination panels. And I guess I got ahead of myself previously, but people who've used these models, here's what they've done. They've either used an average value. They say, you know, I have this population of users. To use this model, I need to define at which point does this degradation path progress such that a failure occurs. If, in fact, that point is not known for certainty, I'll pick an average value. I'm sorry this keeps happening. And then the other instance, though, is let's use worst case. And I think that's what most people do. So what we did, Peng Wang and myself, and this is one of many papers that's written but has not yet been submitted to a journal, we extended Meeker and Lu's model. Meeker and Lu's model already relied on simulation to do the reliability estimation. Concurrent with the simulation to estimate time to failure, we drew random threshold values from some defined probability density function. We assumed that, in fact, we could characterize that, and we then were able to very quickly and efficiently extend the model. This is just a subset. We did probably hundreds of different test cases. And I'm going to completely ignore the stuff on the bottom part of this slide. But we looked at many different instances. Is the random variable capital D, and what's capital D again? That's the failure threshold. That's the point at which the degradation path progresses far enough along, a failure occurs. Maybe it's uniformly distributed, maybe it's normally, maybe it's log normal. The previous work, or previous value, was at the mean, the median, the lower bound, etc. We explored all possible different conditions, but we saw some common results. Now, I don't know how this is going to work with the camera, but if in the past the mean value was used, what happens is that you would, let me remember. You would overestimate the reliability initially, and then finally underestimate the reliability. If you're using the mean, it makes sense that on average, if we look at the whole curve, but the point is, most of the time, we're not concerned, I'm talking about real problems, with this entire time frame. We're concerned with these up here in the upper left-hand corner where reliability is high. We normally are not going to choose to use a system or component and operate it till the reliability is 0.2 or 0.4. If in fact the reliability was that low, we wouldn't use that component at all. Now, the other instance is when the previous value D, a lower bound was used, or an extreme value. That point at which some of our applications or consumers would begin to experience a failure. Now, if that was the case, and here we've made certain assumptions, as I said, we've done many different instances, what we would see is that we would be very pessimistic in our reliability, and sometimes very much pessimistic. Meaning, what does it mean? Well, worst case, the supplier thinks their product is less reliable than it really is. That's not always bad. That's not always bad. That may push them to make a better product, but it could also, in some instances, push them to over-design, spend more time in design and manufacturing that might be warranted if, in fact, there is a firm fixed reliability. Also, it might cause them to make poor estimates on spares, logistics, management, maintenance planning, and other things. So we were able to extend this. It wasn't a significant amount of work, but I think it was an advancement in using degradation modeling. We did some similar work, which I won't talk about, on some of the other parameters in the degradation model. Okay, now, here was a major part of Peng's dissertation. Even if vector Z is in my degradation model, so in other words, I can predict for different environmental stresses, it still assumes that it's fixed or stationary. Now, let me make a distinction. We could have temperature cycling. Now, that's not fixed temperature, but nevertheless, I can characterize that cycle using fixed parameters, the difference between high and low, the frequency, the amplitude, etc. So I can input that into my model as if they were fixed environmental stresses. But what if I have step stresses? What if I have ramp stresses? What if I have even this random type of stresses? And that was kind of the extension we wanted to do. And here would be an example. This, in the simple example, I have just one stress, Z1, but it's changing with time. And as this changes with time, this degradation path, as this stress shifts from this level to this level, is going to accelerate more quickly towards that failure threshold. And that was the next issue we wanted to work at. And furthermore, let me emphasize, we developed a general model such you could have Z1 changing with time, Z2 changing with time, and additional Z's changing with time. We used a theory, and that's the right word for it. It's a theory. It's been shown empirically to work in many instances. There might be other instances where it's not, called cumulative damage theory. And the way it works is this. Okay, I'll try to do this quickly. From this time to this time, there is no change in environment. So I have nothing to worry about. And in fact, I can characterize the cumulative distribution function, capital F. And capital F would be a function of Z1. Again, I'm limiting from here to here. And I'm sorry, this is unclear. This whole stress is Z1T, but this is level Z1, Z2, Z3. But now I'm going to set this equality where I have an unknown called T1 prime. So I have the cumulative distribution function. So if we think of that as one component, the probability of failure, by thinking of a population of components, we can think of it as the proportion of components that have failed. And I'm going to take the same model, but input the higher stress level. Now keep in mind this model will have a series of parameters that are unknown. We need to solve for them eventually. But there's an unknown here, T1 prime. The meaning of T1 prime is this. T1 prime would be the equivalent amount of time if it had seen its entire life at stress Z2 instead of Z1. Meaning, therefore, I solve for Z1T. I need to invert this function. And here I just put in its general sense, T1 prime is equal to that value of T, semicolon, such that this function holds true. I don't know if I explained that clearly. That was a very quick explanation. But now as time goes on, if I have a time I care to evaluate between T1 and T2, the way I evaluate it is I take my actual value of T, subtract out the value of T1, which was the actual time spent at stress Z1, add in time T1 prime, which is the equivalent amount of time as if it had always been in stress Z2. And since I do that, then I can just input Z2. Now, this carries on again and again. I then need to have a T2 prime. T2 prime would be the equivalent amount of time all the way up to shift T2 as if it had always seen the time in stress Z3. And I can carry on for as many stresses as I have. This makes the previous likelihood function, which I used to determine the parameters, which was already kind of complicated and confusing, much more so, but nevertheless we did that. Here's a simple example. I have two stresses, temperature and humidity. Now notice they're both changing, but they don't necessarily change at the same time. In other words, temperature changes here and here, humidity changes here and here. But to use the model, we simply need to create these time scales such that when any one of them changes, we create this, what we define as tau 1. We won't go over this, but this was the likelihood function that was developed by El-Sayed and Iqbali. We needed to extend that because that went from the case where z's were always constant. Now z's are changing with time. So we had this messy function, but computers are nice. And we were able to minimize this likelihood function and determine the parameters of our model. And in fact, through some simulations, we were able to show that it's a viable model. I don't know if it's the correct model for all applications. For some, we maximize the likelihood function. Thank you. Although when I looked at some of the earlier results, I wasn't sure. But no, we maximized the likelihood function. This is some example we used. Let me see if I can, let's look at unit number 4, I suppose. Humidity shifts later on from a value of 1. These are normalized to 1.4, and we see the curve increases more dramatically. But here we notice every single unit has different environmental profile. They all shift at 100. I did that to demonstrate. But notice unit number 1, which is here, we had 0 and 0. Those are normalized values. It shifts to 1 and 0. Unit number 2, 1, 1, shifts to something else. So I have observed this overall pattern, but every single unit in the pattern is exposed to different environmental conditions. I developed a general model. The general model has different unknowns in it. Of course, the purpose of the likelihood function is to maximize that such that I can determine those unknowns. This is a graph of the different environmental conditions. I was able to solve. This is for some light intensity data that Hussein Iqbali generated. I was able to develop this general model. The problem, however, is how do I use that general model? And I have to go right back into the cumulative damage theory. In other words, I'm not coming up with a model that you can input directly to estimate the reliability. I need to go back into the cumulative damage theory, computer reliability function up into time 100 when the environment's all shifted, and then another function beyond time 100. And the details, although cumbersome, are easy to apply. I mean, cumbersome, there's many different aspects to it, but straightforward once, in fact, we've determined the parameters. We did something similar for multiple step stress, for ramp stress. Well, we cheated a little bit on ramp stress. For ramp stress, we said we could model it as a step stress, and then we kept shrinking the size of our steps until it looked like a ramp. We then looked at the case if our stresses become random variables, and we didn't do anything tricky here. We just extended our stress vector. We doubled it in size. We used the mean and the variance of this random stress. Then we tested the significance of the various parameters, and if it looked like the variance was significant, it was inputted itself. This is the variance of a particular stress level. In other words, temperature might be random. We have some stationary temperature with a mean, but it's varying around that mean. What we want to determine is, can we approximate that by the constant amount? Many times you can. In other instances, though, that random variability may accelerate the degradation path towards its failure threshold, and so we incorporate the variance directly and explicitly into the model. Now I'll just very quickly and go over some of the remaining things. The issue that we've really just worked on is now I have n components. Each component has a degradation path that I just described. I want a system reliability prediction. If they're all independent, easy. I can look in any reliability textbook, and if it's a series system, it'll be the product of the individual ones. However, if they're dependent, and this is going to make it seem, well, if they're dependent, the issues get much more complicated. If, and I'm not implying this is ever easy to do, if I could get a joint probability density function for each of these degradation paths, then in theory I could set up an equation. And this looks confusing, it's not. What I'm saying is that I have n different degradation paths. For this system to be reliable, it means x1 has to be less than d1, x2 has to be less than d2, et cetera, et cetera. I have these n components. Each of them have their own degradation threshold. And for the system to work, none of them can pass the threshold. Now, if in fact each of these paths, and this is all for fixed t, this would be the random x2 degradation measure at fixed t, and is it in fact less than d2? If they're independent, it's easy. If they're not, then we need to come up with this joint probability density function that looks good mathematically. In practice would almost be impossible to do if all you had was data with which to estimate it. So we came up with some approximations. We, using normal and log normal distributions, seemed to give us some pretty good results, and it indicated, just as you might think, if the degradation paths are dependent, in other words, if one is high, they all may tend to be high, that the reliability will suffer. In fact, I guessed, we love this independence assumption. Take a statistics class, independence. Makes things easy. And in many instances, it's a good assumption. But in reliability, we make that assumption all the time. I do. But there's other examples where it's not necessarily a good assumption. And here's an example. We're exploring just that case. And in fact, we found out that you might tend to overestimate reliability if, in fact, they are dependent. Here's where I'm trying to go next. We have a system. We've said we can anticipate failures with these degradation paths. Now I want to know, and let's say we're doing that. We have sensors, and now with MEMS sensors and things, you can get sensors very small and they're inexpensive. And maybe through wireless communications, you can get the data, and you can get efficient data processing, so I can be updating my model. I can be updating my model in real time, constantly updating projections, not of the anticipated time to failure, but the whole distribution of anticipated time to failure, the mean residual life. The issue is, and I don't claim to know the answer, but I view this as potentially a major opportunity for additional research, is how can I use this model to, in fact, minimize the overall maintenance cost, if that's what my desire, of the system. Where do I place these sensors? How often do I read the data? How often do I update the model? And how are we going to do this? We need all sorts of things. We need technology. You know, I can show mathematically that if we can measure this degradation path, I can anticipate failure. But if this system is operating out in the field, let's say it's your car, it may be going on, this degradation, but if I don't know about it, then I can't use it, right? But if I have a sensor installed, I perhaps can make these measurements. So I need technology, signal processing, I need the models, and what we just talked about is one of them, the degradation modeling. You know, I need to generate this concept. If you combine these all together and do it efficiently, perhaps you can achieve levels of reliability much beyond what currently, even for the most reliable systems. Think about it. If you can, we're dealing here with anticipating failure. I remember when I started working as a reliability engineer, people say, oh, tell me then when the system will fail next. And I used to laugh and say, well, that's a dumb question, because it's a random event, and I can't say for sure when it's going to fail next. And so some people say, well, you're not a very good reliability analyst then. But we're getting closer to that. Yes?
David, is anybody applying this to biological systems?
Oh, I have no idea, because I don't venture into that arena, although I'd love to. But I don't know. I don't know. I think that would be fun to find out. And let me just, and this is the final thing. I alluded to this, and actually I had all these slides, and Professor Smith said I'll never get through them all. Of course, I'm from the. Yeah, I'm from the north. They say we do things faster. I don't think it's true, because I'm from the northern part of New York State, where things slow back down again when you get up outside of Syracuse and things. But anyways, it looks like I'm going to finish with plenty of time. Here's the final issue. This is something I've defined for a graduate student. But I want to turn this into an optimization. And people who've worked with me, which include several in here, know I somehow take all problems and try to force them into an optimization problem. And I think this is an optimization problem. It's similar to what I just said on the previous. Let's say I have a system with hundreds and thousands of different degradation paths. And if I can efficiently monitor them all, process the data in real time, anticipate failures, I can potentially have a very reliable system. But realistically, I probably can't process. I can't analyze them all. Not only that, it's probably not wise to. Sensors, of course, can fail themselves, keep in mind. Because I probably have some dominant mechanism. I have some maybe that don't happen as often as I can ignore them. And so we want to turn this into some sort of optimization model. How do I optimize reliability where my decision variables are the placement of the different sensors and you know, they may be monitored in real time, but there's also another decision variables. How often maybe I'm going to look at this data and make a judgment as to what to do. That doesn't really say too much other than, but we're trying to formulate the problem different ways. And this is the most simplest case. I have some sort of constraint. I can only put so many of these sensors on. Potentially each degradation path has a different sensor with a different cost associated with it. And I want to look at the placement of these sensors where yi represents a 0, 1 variable. It says I will put a sensor in location I, and 0 says I will not. And this is the optimization problem. I don't have a solution. In fact, I haven't worked on it much more than this. I identify this, though, as an additional research issue, something that as we take this degradation modeling concept and continue it on, something that would make a nice piece of research, and I hope, anyways, would also be practical. In other words, would improve the performance of real systems. And I don't have a conclusion screen. I usually never do, because I usually run out of time. But that concludes my talk. Can I entertain a few questions? Okay. These are hungry people here. And they
I followed most of what you said.
Okay, thank you very much. Oh, I'm sorry.
I was just going to ask, do you think being able to tell when a system will fail will make the reliability 100%?
No.
Can you get to that point?
You know, boy, you can always dream. You can always dream. And, you know, I said in my in some earlier remarks that, you know, we're getting close to the point where if someone says, well, when will this fail next? We can stop saying that's a silly question because it's a random event. We can start giving answers. But the answers still aren't deterministic, and the answers still aren't with some degree of confidence. And furthermore, let me particularly emphasize, what I've just discussed here today is for one class of failure mechanisms. There's many failure mechanisms that will not behave like this. And in fact, you know, as we had these cave meetings over the last several days, we can look at the solder connections of an electrical component mounted to a circuit card. The solder connections fatigue with time as it's cycled, and we can monitor them as the degradation path. The electrical component itself generally fails catastrophically. It means it's operating just fine. Then an open or short or something occurs. So within a system, we have some that can be monitored this way, some that can be not. His question is, will we get to 100% reliability? Well, that's the goal, I guess. That's the goal. Yes?
David, I guess I would just be surprised if somebody is not looking, you know, back up. We have so much going on, the development of medical devices, the artificial heart, artificial kidneys, all sorts of artificial components for the human body, artificial arteries. I guess I'd just be surprised if someone isn't looking at the reliability issues related to those components in the human body. I know it's a complex thing to do, but it seems like this approach would be a natural for that sort of thing.
Yeah.
I think a lot of interdisciplinary work between engineers and medical people who normally don't talk to one another.
Yeah, absolutely. And but, you know, some people in here know, some of the very early work in reliability engineering, including what we call the proportional hazards model, was developed by people working on health type issues. And what they were working on is if I have a cancer patient and they were a smoker versus not a smoker, they're this age versus this age, how long will they live? And then people like me have, you know, extended that to hardware. So I'll look into that. And, okay.
You had a very complicated likelihood function there, and you got about 5 parameter estimates. Did you guys use a computer to get the answers for those estimators, or did you do it analytically?
We absolutely used the computer. We would not be able. We used a pseudo gradient search. We weren't computing actually gradients, but estimating gradients, searching to the, I keep saying bottom, but the top of this very ugly likelihood function. We're now, and that's the beauty of computers. I can get this horrible likelihood function that I could never solve analytically. And I can search around, and of course, not to belabor the point, but something as you I'm sure would be aware, often those likelihood functions have a plateau on top. Meaning that some of those parameters I could change and not vary the overall results dramatically. And furthermore, even though we did not do it here, it's important to test the significance of those. Okay.
Okay, thank you.